So welcome all IEM and UEM family members. Hello again. So today in the afternoon meeting, the presentation is by Dr. Jyotirmoy Haloi, who is from the Civil Engineering Department of University of Engineering and Management, UEM Jaipur. And his topic is fiber reinforced polymer pultruded profiles and their applications in civil engineering. Wonderful. I believe that there are many keywords that you have used. I'm sure that you will be explaining all the keywords and proceed with a wonderful presentation. It seems very interesting. At least I feel it's very interesting and I will pay a lot of attention. I will request all of you to kindly post your questions in the questions box. And if you would like to orally interact, you can raise your hands so that I can unmute you at the end and you can also talk to the speaker. Okay. So thank you, Dr. Jyotirmoy. You may kindly take over from here.
Thank you, sir. So a very good afternoon to everyone. So today's presentation is all about fiber reinforced polymer pultruded profiles and their applications in civil engineering structures. So I'll start with a general background of fiber reinforced polymers or FRPs, their types, then their uses, and some material properties, and some of the research works I have done in my PhD during my PhD. So I'll begin with what is fiber reinforced polymer. So fiber reinforced polymers are generally manufactured by embedding different types of fibers like glass fibers, carbon fiber, or aramid fibers in a resin matrix. The types of matrix or resins are mainly epoxy, then polyester, vinyl ester, and they are formed into different shapes. So in fiber reinforced polymers, the fiber concentrations are mainly greater than 30% by volume. So various types of fiber reinforced polymers, or in short, I can say FRPs, are available in the market or in the domain. So these are mainly FRP parts, which are mainly used for as a replacement of conventional steel reinforcing bars. Then we can see the FRP filament mats or sheets, which are mainly used for retrofitting purposes. Then FRP pre-stressing tendons, pebbles, strands. So these are typically used in bridge applications. And lastly, and the FRP pultruded profiles. So you can see the FRP sheets or FRP mats are mainly used for retrofitting and rehabilitation of old, or like some after some earthquake, if some structure, some deformation is coming up, then we need to rehabilitate those structures. Then in those cases, we retrofit using these FRP mats or these sheets. Next is the FRP parts. So in order to reduce the corrosion in FRP in steel or in reinforced concrete, we generally use these FRP bars in place of the steel reinforcing bars. And third one is the FRP pultruded profile. The FRP pultruded profiles is now gaining tremendous popularity because of their manufacturing processes and the strength properties which they impart. So FRP pultruded profiles are nothing but fiber reinforced polymer only, but here the manufacturing process is like pulling the fibers through a liquid resin bath, and they are after that they are cured in a heated metal die, and we can get into the required shapes and sizes. So this is the pultrusion process. We can see in the first the below the left figure. So different fiber architectures are being pulled through a heating equipment, which we can call as a heated metal die. Then you can get the desired shape and can cut into different lengths. So in this figure, you can see the FRP Builtin profiles. So various types of architectures are mainly used for for production of these FRP Builtin profiles. These are mainly combined mat, then this unidirectional roving, then continuous strain mat. Also, one important thing is that in civil engineering applications, mainly glass fibers are used due to their cost-effective nature. So, in Builtin profiles, the fibers are oriented mainly like this. Unidirectional roving layers will be placed in between different fiber mats, then fiber strands, and we will get the desired shapes. So you can see in market various shapes are available. So their uses are mainly like, as I said, it has gained tremendous popularity because it is now replacing the steel sections due to different advantages, which I'll be coming in the next slides. So throughout the world, different pedestrian bridges, different buildings, then FRP roofs, all are being manufactured and used nowadays. Like in the last 2-3 decades, it has gained momentum. So, what are their advantages and disadvantages? Because this has got tremendous popularity nowadays. So, main advantages are like they have high strength to weight ratio compared to the other conventional materials like steel or like concrete, and they always offer better corrosion resistance than other materials like steel and concrete. Then they have good resistance to frost and de-icing salt. Also, they are having lower maintenance cost, and they can be easily transported and quickly installed at the site. However, certain disadvantages are there, which are actually hindering their widespread applications. And these are some concerns to the structural designers. Mainly, their lack of ductility and their low fire resistance. Now, if you see the advantages are like this, if we see this figure in the left side, this bridge was manufactured, and actually it was installed within a period of around 2 hours, which is actually very less. So it can save a very like the construction period. It can save and it will save the cost also. So these FRP bridges you can see, these are mainly prefabricated and they were transported and they were installed at the site. So this is the first bridge which was constructed in Russia, which is fully of FRP. So it was installed within a period of 1 hour. So you can see how it quickly be installed at the site. Some other structures are also being built, like the FRP cooling towers. So this FRPs actually provide a good corrosion resistance. So that's why these FRP cooling towers were manufactured using these FRP profiles. So in many of the buildings now coming up and already have been constructed, they use FRPs as structural members and like non-structural members such as claddings, etc. So these also gives good aesthetics to the structure. Then FRP prefabricated buildings or prefabricated small housings are also coming up. Due to they are lightweight, these buildings can be easily transported, and can be delivered at the site. So there are other applications are also here, like FRP piles. So these FRP piles were used like for underwater construction due to their advantages in corrosion resistance. So these are typical applications. Now coming to the material properties. If we see this table, we can see the GFRP here. GFRP means glass fiber reinforced polymer. If we see the density, it is around 2100 kg per meter cube. Whereas in case of steel, it is around 7800 kg per meter cube. But compared to steel, the tensile strength, if we see, it's more better than it can go up to like 720 Newton per mm square in case of GFRP. And if we say about CFRP, it will go even higher, like 3400 Newton per mm square. But their density is also very less compared to other materials. So yes, these are having high strength to weight ratio. However, one disadvantage in these FRP profiles are like they are highly autotrophic. That means the strength properties are like different in it may differ in different directions. So as we can see, when the fiber orientations goes from 0° to other angles, then the strength reduces. So it's a kind of disadvantage. And now I'm coming to the tensile behavior of the FRP. So I'm considering this GFRP. So GFRP actually these are brittle material having no ductility, and they always give like linear elastic stress strain behavior or low displacement behavior. However, in case of mild steel, this is a mild steel, this stress strain curve. We can see that this after this yield strength, it goes for certain elongation. So this is called a ductility. But in case of GFRP or CFRPs, we don't get this kind of behavior. So there is no, it will be very misleading if we say some yield strength is there in GFRP. So we always say like ultimate strength of GFRP or CFRP. So coming to the compression behavior. So the compression behavior is also similar to the tensile behavior. These are brittle material, and the stress strain curve is linear elastic up to failure, and there is no ductility. So coming to fire behavior. So fire behavior is a major concern for the structural designers, structural engineers, because the glass transition temperature is around 120 degrees centigrade for GFRPs. The glass transition temperature is a point from where the solid or the glass will start to like behave as melted or like semi-solid kind of thing. So when these GFRP profiles are exposed to elevated temperature, the strength reduces. So we can see from this figure. Now coming to the structural behavior, the main failure modes we see like the instability phenomenon always predominates in case of both compression and flexural members. We can see now the buckling patterns. However, there is another type of failure which is a great concern for the researchers is the wavelength junction failure. The wavelength junctions in GFRP profiles we see are a weak point. So in many cases, you will find that the GFRPs actually fails in the first they will fail at the wavelength junction, and other failures will come later on. So this is a great concern. Now different design guidelines have come up throughout the world. or designing or for designing these FRP structures. However, the design, they have considered whatever the partial safety factors or other factors. There are great variations actually, and we need some consensual design code in order to overcome the cost, so that we can get some cost benefit. And one important thing is that in India there is no design guideline for FRPs till now. So I think we should work on that. So the design guidelines, actually they have adopted the design expressions from different literature, which are still in the development processes. Now coming to the sections and products available in Indian scenario. So recently, like from past 2 decades, many Indian manufacturers have come up for this for manufacturing these FRP procedure profiles. So many grating structures, then FRP beams, columns have been manufactured. You can see FRP footpaths. These FRP footpaths have been now widely used as an alternative to the conventional concrete footpath throughout the northeast region of India. Also, different FRP buildings, prefabricated buildings have come up where FRP panels and beam members have been used. So different other structures are also coming up. Now, coming to the research thing, I have adopted this I section. If you see in the top right figure, I have adopted this I section, which were used in manufacturing this FRP footpath. So some experiments I conducted during my research work. So mainly, I conducted scanning electron microscopy, then burn-off test, then tensile compression, then incline and interlaminar shear test. So for my study, I considered 6 different shapes and sizes of these FRP full-fluted profiles, and these are mainly this I section. If we see the I section, then 3 different channel sections, and 2 rectangular hollow sections. So different procedures are already there to conduct these experiments. So I followed these codes. So from scanning electron microscopy, it was observed that the FRP profiles were having randomly distributed defects or voids throughout the profiles. One particular observation was that a continuous defect was observed in the previously described this I profile. Here, one continuous defect was observed. The width of the defect was around 146 micrometer. So this may hamper the behavior because the micro cracking may start from this crack. So this can be the remedies maybe during the manufacturing process itself to reduce the defects and faults. Then burn-off tests were conducted. So these tests were conducted mainly in order to find out what type of fiber architectures the manufacturers were using to manufacture the FRP profiles. So after burn-off test, during the burn-off test, the FRP profiles were like we made bronze specimens of sizes 25 mm. Then we heated it up to like 565 plus minus 25 degrees centigrade for around 6 hours. So after that, we got that the manufacturers mainly used the unidirectional rolling layers, then combined mat and continuous strand mat. In each case, the unidirectional rolling layers were sandwiched between the continuous strand mat and the combined mats in all profiles. The fiber contents were also calculated. So we can see the fiber percentage is a range between 68 to 74%. So this is the typical. So these are the typical images. Now coming to tensile test. So this tensile test were conducted, and we used like strain gauges, then extensometers to measure the strains also. So we can see the failure patterns in the second figure. You can see delamination actually the main failure pattern. And also from stress strain curve, we can see all profiles showed linear behavior up to failure, and no one showed any ductile behavior. In case of compression coupons, the main failure patterns were delamination only. However, their stress strain behavior were in a combination of linear and nonlinear patterns. This may be due to the reason because when we carry out tensile tests, the fibers mainly take parts in the strength. However, in case of compression, the matrix also took part in giving the strength. So the stress strain behavior of matrix or the regime is always nonlinear. So it is a combination of both. We can see. So other tests were also carried out, like intense shear test, which were conducted using the procedures given in Hoskinson. Then interlaminar shear test. Now coming to some of the material data, if we see the ultimate strength of the material was in the flange, it was around 345 Newton per mm square, whereas in case of web it was around 323 Newton per mm square. So which is quite comparable to the steel, and however the elastic modulus were around 1/7 of steel. So these are some typical data which I got from the material characterization test. Some other experiments were also conducted. This is a wave papering experiment. So why I carried out this experiment? Because as I said previously, the FRPs are orthotropic. So in each direction there will be different strength properties. Also under compression, the waves of the FRPs are very much susceptible to this crippling failure. Crippling failure always occurs when we use these FRPs as beams, and when it comes under transverse, concentrated or bearing loads. So these experiments were carried out, and these were published in the journal I have shown you. So also we can see the load displacement behaviors are mainly linear elastic. Some ductility is seen, but it is the point. If we see the failure point is the mainly wave flange junction failure. After that, we should not actually consider the strength whatever it is giving. So these are some proposed equations which were published in the journal I have shown. And this is the footpath. Actually, I conducted the experiment. This is a 4-point bending test, and we reported it to the Public Works Department, Assam government. And based on that, they used the FRP cover, FRP footpaths as drain covers throughout Guwahati city. So that is the thing. So thank you.